Hello, everyone, and welcome once again to a TVS colloquium. Today we have the pleasure to have Alexey Bobrick. He will tell us about peculiar transients. He's a fellow at Monash University. Anyway, this will be very interesting, so please take it away, Alexey.
All right, thank you so much, Priscilla. Thanks so much, everybody, for being here. It's my great pleasure to talk about one of my favorite topics. Uh, it's about peculiar transients in the era of LSST. First, I was maybe curious, maybe people might want to know what actually we mean when we talk about transients. Here are two images actually of a relatively nearby galaxy M82. So if you um, can visualize it, it's approximately of the size of half of the full moon. So it's actually a pretty nearby and pretty big chunk of the sky, and it's a combination of ultraviolet light and optical light. This is the image of the galaxy taken in 2013, and then this is the image of the galaxy taken in 2014. And a sharp eye might notice that, bam, there is one more bright spot over there. So that's apparently a supernova explosion. Um, so basically, this is what we mean when we talk about transients. It basically is everything that changes on the sky in the sky, and there are many things that are changing, and one needs to have really very sharp eyes to be able to keep track of them all. Um, in fact, there's quite a big variety and abundance of these transient things that happen over there. So this plot on the left is from a review by Matt Nicol of all the different transients, these sort of bright spots that have been spotted with various telescopes in the sky. And the bar plot shows the number of new detections every year. And we see that, well, some time ago, detections were counting maybe in maybe a bit less than 100 per year, but now recently, especially from the start of the all-sky panoptic surveys such as Pan-STARRS and ZTF, we robustly have approximately several thousand or almost 10,000 of transients identified every year. And on top of that, we also have classifications for approximately a couple of thousands every year. Um, Another way of seeing that is a cumulative plot that's shown on the right. So it's again number of detections, total number of detections made over time, and we see that it's been steadily growing, maybe following almost Moore's law, maybe even going super exponentially, as some people say. So every year we have some doubling or multiplication of number of detections, and it only keeps growing. So you can see that right now we are somewhere in the order of like about 10,000 detections per year. And the thing is that with LSST launch, we expect to have of order of 1 million detections per night. So we are somewhere in 2025, and on this diagram, we're somewhere here. So LST will really make the transit sky very interesting. And then the other thing that this plot shows is that also over time we've becoming better and better at detecting things that are faint. So in this case, it's a class called superluminous supernova, but still, the longer we observe, the more unusual things we discover. So when one thinks about all the diverse types of transients, one can classify them based, for example, on their duration and peak brightness. So this is a plot inspired by the plot introduced by Mansi Kasliwal once upon a time. And basically on this diagram, you can see transients that are very well observed. For example, core collapse supernovae, they are very bright, reach luminosities of about billion times the solar luminosity at their peak and last for give or take a couple of months. Um, then there are superluminous supernovae that I've mentioned that are particularly bright. There are type 1a supernovae that are thermonuclear supernovae, which are also extremely well studied and are used in cosmology a lot. But also you see that the fainter you go, the more different types of transients you find. There are these gap transients. There are a variety of peculiar transients over there that are rare and unusual. There are type 1a explosions, which are not exactly type 1a supernovae. There are predictions for accretion-induced collapse, which is another process that happens over there. There are luminous red novae, which is yet another thing. So which are just faint emerging things. And I guess here I want to highlight that the more things we can see, the higher the diversity of the things we discover. So um, the fainter, there are more ways of producing a faint transient than ways of making the brightest transients. So only one thing makes the brightest thing, but um, many things can make the 100th brightest thing, if you like, or sort of things that 100 times less bright than the brightest thing. So another way of looking at it is by thinking about all the types of things that are happening in astronomy. So so on the top, there is a diagram of binary stellar revolution. So from a review by Jean Van Haan, written recently. And this review has been basically trying to summarize all what that we know about the evolution of binary stars. All right, so stars usually start in pairs. They can have some separation. They can expand and interact with a companion and therefore, for example, merge or go through stable mass transfer, so interact. There are some products of such interaction, and the stars can then further interact with the products. So this diagram is just to show that there are really many things that are happening. And some of these things might eventually explode and produce a transient, or they might merge and produce a transient. So all these symbols that show something like an explosion are various types of transients. So that is the sort of reality that the binary stellar evolution community deals with. At the same time, there's also the reality that we observe when we look at the transient sky. We see these different types of classes of transients that we observe over here, and these classes have been discovered over time. And I guess that probably in the long term, it's very likely that the classes that we observe should be somehow matched with what is happening out there, um, according to the like stories of stars. Um, from this point, I would like to jump into one specific type of object that produces one specific type of peculiar transients, and then show you the variety of these things that might be happening. So the specific type of object that I want to talk about is actually are actually white dwarf neutron star binaries. So this is a artist's impression of one such white dwarf neutron star binary. It actually is a long-lived source. It's a visualization of an ultra-compact X-ray binary called for you 1820 - 30. So in this case, there is the white dwarf over here that has approximately the mass of 0.067 solar masses. It's been highly stripped of its original mass, and now it's a lightweight remnant that's left over there. And it's losing mass to the neutron star companion, and the mass is forming the accretion disk if you follow my mouse, and then the accretion disk heats up to temperatures that emit X-rays, and therefore this binary is observed as an X-ray binary, and it makes an orbital period within approximately every 11.4 minutes. So these binaries are actually formed through their own story or through their own evolution. So there are several, approximately 3 or 4 ways of making these white dwarf neutron star binaries, and this is just one of them. It basically is not to go in depth in here, but just to show that, yeah, it started all with 2 main sequence stars, and then there was a series of interactions, and now we are left with this sort of white dwarf neutron star binary. The following slide basically summarizes almost all we know about the physics of white dwarf neutron star binaries, as shown in this picture. Um, Initially, these binaries form detached, so there is a white dwarf and a neutron star, and they are not interacting. A subset of those are at separations sufficiently tight so that the binaries will spiral in within the Hubble time due to the emission of gravitational waves. And once they spiral in, there are interactions start, and there are 2 possible outcomes. One of them is taking place if white dwarf was of low mass. In that case, the binary would evolve over long time scales and would appear as this ultra compact X-ray binary that I just talked about. In the other case, if white dwarf was massive, the system would undergo a merger and produce a faint red transients add enough to our diverse transient sky. So there are quite good rate estimates for the white dwarf-neutron star binaries at all stages of this evolution. So there's quite a large number of detached white dwarf-neutron star binaries observed as binary radio pulsars. The most pronounced of them is pulsar G11416545. It's a relatively young, very interesting object that is actually gonna spiral in Hubble time, and it's very eccentric, and it informs us about the rate of formation of these objects. But generally, there are about 200 such objects that inform us about the rates. Um, they spiral at a rate approximately of 50 to 500 systems per million years per Milky Way-like galaxy. So in our galaxy, we'd have to wait for a long time to see such a merger. And yeah, these ultra-compact extra binaries apparently very rarely form out of the original white dwarf-neutron star binary, so it's quite rare that the white dwarf is a low mass. In fact, the distinction between low and high mass white dwarf is approximately 0.2 solar masses, so white dwarf has to be really low mass to form this ultra-compact extra binary, and well, so the rate of their formation is much lower than the rate of the in spirals of the progenitors. All right, so how do we study them? So here I'd like to show you some simulations of how do we understand the physics of their interaction. And in fact, even I would like to spend a few minutes to just discuss how the interactions happen, because maybe it would give us some idea about, uh, maybe we have some intuition about what really happens during stellar interactions. So when two stars interact, they are first of all affecting each other by their gravitational forces. So stars are sitting in the Roche potential. Roche potential is basically the gravitational potential field of two-point masses that are centered at the location of the stars and have the masses of the stars. So it approximates the gravitational field produced by a combination of two stars. And a given star has a thing or a concept that is called its Roche-Lobe radius. Roche-Lobe radius of a star can be seen as a radius or a volume in which the star dominates the gravity. In other words, if a piece of material is inside stellar Roche-Lobe, its movement is dominated by the gravity of the star which has produced the Roche-Lobe. And if material is outside of the Roche-Lobe, its movement is not dominated by the gravity of the star, and it can, well, move somehow freely. When there is a star with a companion, the companion might make the Roche-Lobe of a given star smaller. So in some cases, Roche-Lobe cuts into the star, so when the star binary is too close, so that the star no longer dominates by gravity its outer layers. In other words, if the companion is close to the other star, it starts to strip away the material from the surface of the star. And this material flows along the equipotential lines and comes to the orbit of the companion. So basically, the star is losing mass. And some authors have compared it to the process of a balloon. If you have a balloon and open it, then there is air fizzing out from the balloon in this direction, just like the stars lose mass to the companion, and well, that mass ends somewhere near the companion. And this process of losing mass is quite sensitive to how deep is the Roche-Lobe inside the star, and it actually follows the exponential law where basically the rate at which mass leaves the star is proportional to the exponent of the ratio between the depth of this Roche-Lobe potential and scale height of the star. Now, there's quite a good understanding of what happens when star loses mass to the Roche-Lobe. I will not go too much into that. If you don't like equations, look down. If you like equations, look up. But the point is that when star loses material to the companion, material usually either lands on the companion or leaves the system. And all these movements of material affect the binary orbital separation. So the equations that we use to describe the long-term evolution of this system actually accounts for the fact, basically for all the effects that take place. For example, how the star changes its radius as it loses mass, or for example, how the material flows once it has left the star. For example, how does the material that has left the binary affect the binary because of the angular momentum exchange. So all of these things are accounted for in these equations, and I'm happy to talk more about them later if anybody is interested. Now, if we want to model these things, usually we want to describe what happens to the material that is lost from the star. So actually for modeling specifically white dwarf and neutron star binaries, we have developed a code which is called oil and water code. And this is an example of actually two stars, a neutron star and a 0.6 solar mass carbon oxygen white dwarf doing exactly nothing. So they go in circle and it's just a demonstration of the code. If we put it towards doing something more exciting, then here's an example of such evolution. So here we see the mass transfer happening between a helium white dwarf of 0.15 solar masses and a neutron star. And you can see how the material from the surface of the white dwarf forms a disk and orbits around the neutron star. And as it orbits, it actually also leaves the disk with angular momentum comparable to the angular momentum of the circularization radius and forms a cloud around the binary. We have been able to do these kind of simulations by representing the white dwarf by two types of particles. One is the type of particle is the one that allows us to model the body of the star, where we don't need that much resolution because the body of the star stays always intact. And the other type of particles is the type that describes the surface of the star, where we put a lot of resolution, and this way have been able to resolve what happens during mass transfer. And the point is that actually the mass that is lost from the binary actually matters a lot for the binary evolution, because if you remove angular momentum from the binary wants to come closer and interact more. And if it wants to interact more, then it probably can transfer more mass. And so it goes as a unstable runaway process. And it might also not go that way if the angular momentum taken away by the material is low. So in principle, measuring the angular momentum in these simulations has allowed us to predict what happens further in the evolution. So going further, this is an example of actually what happens. So this is the plot of a long-term evolution of a binary that actually did not merge. So on the x-axis is the mass that's lost by the white dwarf. On the y-axis is the mass transfer rate. And you can see that initially, when little mass has been lost, the mass transfer rate increases, so the binary starts to interact. But then at some point it reaches the peak value, and after some long time, it never goes any higher and just decreases because the white dwarf actually has been almost fully consumed. So actually that's the plot for a 0.15 solar mass white dwarf. And at the end of the simulation, after several billion years, what's left from the white dwarf is only a 0.05 solar mass object. So it's a relatively like long-lived stable system. In contrast, for example, if you take a massive white dwarf, for example, of 0.75 solar masses, as the mass is lost, as the white dwarf is interacting, the mass transfer rate is increasing to really high values, approximately 10 to the 10 times Eddington mass transfer rates, or 10 to the 4 solar masses per year, or actually in more realistic or more normal white dwarf scale, it's approximately, well, give or take, approximately 10 to the minus fourth portion or 10 to the minus third portion of the white dwarf mass per orbit. So it actually is a very highly intensely mass transferring system at the moment of merger. Um, so, and I think it's kind of almost informative to actually think of mergers like that. So in other words, the mergers don't happen like at once. They don't happen on one orbit time scale. They actually happen gradually over many orbits. And during this time, the mass transfer rate gradually increases until it becomes extreme. In the case of this 0.75 solar mass white dwarf neutron star binary, actually we see that the amount of mass transferred by the time of merger is actually not that large. It's actually 10 to the minus 5 solar masses. So it's not that much. But nevertheless, it's still, in some cases, quite important, as I'll discuss later. So another interesting aspect actually is that typical white dwarf neutron star binaries, they spiral in eccentric. So when they spiral in, they still have non-zero eccentricity. And in fact, their interaction goes in this fashion. So during the pericenter, the donor loses mass, and during the apocenter, the donor does not lose mass. So the mass transfer is pulsed. So in other words, the interaction is happening in pulsed fashion. But actually what we saw from the simulations is that even though mass transfer is pulsed, the disk smears out these pulses. So the disk somehow gets each pulse of the material, but viscous timescale in the disk is much larger than the orbital period, and therefore the material that leaves the binary kind of forgets that it has been delivered in pulses to the disk. Moving onwards, I would like to talk a little bit more about the siblings of surviving systems, basically the systems that actually merge. So white dwarf neutron star binaries, the majority of them merges, as I mentioned before. So there's been quite a lot of efforts in modeling the merging white dwarf neutron star binaries. In particular, it started with one-dimensional simulations where the disk was basically beamed in radial direction and a disk model was used. And in fact, the first predictions of the faint transients from white dwarf neutron star mergers have been done with 1D models. More recently, 2D models have been developed, although since then they have been further superseded by 3D models. Only two groups so far have done that, but I hope there will be many more in the future because these binaries are about to become extremely interesting to many people. So here is a simulation and a video of how a merger of white dwarf neutron star binary can look like. So you can see that neutron star shreds the white dwarf, actually gets the material faster and faster, and basically what was a spherical white dwarf just a few moments ago is actually becoming a very elongated disk, one could say. So carbon oxygen disk as opposed to carbon oxygen white dwarf we see here. And just for completeness, in case you might want to see how it looks like, here is a more massive white dwarf of 1.2 solar masses, oxygen white dwarf, so 2 times more massive white dwarf, that merges more violently and faster compared to the carbon oxygen white dwarf. So more massive white dwarfs are smaller, they react to mass transfer more intensely, and they merge more violently. And you can even see that white dwarf launches spiral waves, and there's this optical effect that it almost keeps on spinning after the last frame froze. All right. Moving onwards, I'd like to speak a little bit more about how the light gets generated in transients, and especially in thermonuclear transients like the Japanese supernovae. So usually people think of it as follows. So for example, if you have a nuclear supernova, thermonuclear supernova that has just happened, usually would have a lot of ejecta, for example, like, well, give or take maybe 0.8 solar masses worth of ejecta that would be well mixed up with radioactive nickel 56. And the thing about nickel 56 is that it is an unstable isotope. So nickel 56 is synthesized in mergers because it's close to the iron peak, and nickel 56 decays on the time scale of about 9 days. And when it decays, it turns into cobalt 56, and later cobalt in turn is also unstable to nuclear decay, and in about 111 days, it turns into iron 56, which is stable and in abundance. In fact, these thermonuclear transients are the reason why we have iron in our blood, and it's actually a very common process for its production. So, and the way to think about it, I suppose, is that all this decay of nickel happens inside the ejecta. So there was 0.8 solar masses of ejecta. Inside it, these atoms are decaying, and then they are depositing the energy from the decay in the form of positrons and gamma rays right into the surrounding material. And this surrounding material heats up and starts to glow. Not only that, it's also expanding. So you kind of get an expanding material that gets hotter and is still expanding. So, and therefore luminosity of this molecular transients, well, peaks and shows the energy or looks bright as a result of this expansion, the material becoming optically thin eventually, and the nuclear decay that happens all together. So that this is what generates the light curves of thermonuclear supernovae. So specifically for white dwarf neutron star binaries, by doing these simulations and by checking the nuclear evolution in the disrupted white dwarfs, one can infer that if one considers more massive white dwarfs, the amount of nickel 56 is produced in sort of in a sensitive fashion more for higher mass white dwarfs. So for example, if you take a relatively normal 1.2 solar mass white dwarf, one can produce approximately 0.7 or 0.8 solar masses of nickel 56, which is not a negligible amount. And even relatively more common and almost boring 1 solar mass white dwarfs still produce quite significant amount of nickel, which is about 0.03 solar masses. So it's relatively faint for it to be considered a bright event, but in fact, we have tried synthesizing the light curves, and we found that, well, yes, typical dwarf-neutron binaries actually reach luminosities, so bolometric luminosities of about -15, which is not very bright. Typical supernovae are somewhere over here on the plot. Well, somewhere over here. But some of the models actually can be quite bright. So I mean, the point is that, yeah, well, these actually mergers end up being relatively faint. And actually, by considering the spectra or synthesizing the spectra, we found that they are most likely corresponding to so-called type 1a X supernovae or faint end of them. So actually, the faint end of a rare type of a supernova. But also we made estimates, and actually, if you take LSST bands for one such typical transient and consider the peak, actually this is what LSST would really like, because they are not so bright but sufficiently bright for LSST to see them, and on top of that they are also happening relatively slowly, so they don't rise and disappear like very quickly. They actually last for easily for tens of days, almost a month. So our expectation actually is that LSST will be able to see thousands of such transients per year. And in fact, it's actually very interesting to see what will happen when LSST will discover a class of transients that is very faint and slowly evolving, or not. If it doesn't discover it, it will be also extremely interesting. All right, so moving onwards, I want to talk a bit about globular clusters. Globular clusters are groups of about 1 million stars in which the stellar densities are so high that the interactions between stars produce quite a lot of stellar exotica. As a matter of fact, here is an X-ray image of a globular cluster 47 TAC, which is one of the biggest large globular clusters we see in the sky. And the X-ray image shows the different X-ray sources in the cluster. And we can see that there's a lot of X-ray sources in the center of the cluster and not as many outside. It means that global clusters are really good at producing X-ray sources. And in fact, the system that I showed earlier for U1820-30, the artist's impression of white dwarf-neutron star binary, actually is a system that actually has been produced inside the global cluster. So I'm talking about it because LSST will be useful here too. Remember, I mentioned that systems that merge actually first have some certain evolution that goes with mass transfer rate growing, and only then the binaries merge. So one of the calculations one can make is basically checking how long time does it pass till the binary from some point in the interaction till the binary actually merges. For example, this is a curve showing such time scale for different masses of white dwarfs. For example, here is a mass which is merging robustly, 1 solar mass. Here's the mass that is just on the boundary between stability, 0.2 solar masses or so. And we see that systems can merge between, 10 to the -5 of a year, which is, yeah, well, I mean, you take less than like some tens of minutes, and some other systems which are merging on time scales of, like a day, or some others that are merging on time scale of a year. So LSST will be looking at the same patch of the sky about once every several days. So in fact, just so LSST will actually capture the process of a system going towards the merger before it actually goes off as a supernova. So I think this data will be extremely very interesting, at least for the white dwarfs of about 0.5 or 0.6 solar masses. And if LSST sees thousands of these transients, then even for 1 in 1,000 of such transients, it will also see the rise towards the supernova early on. So I think it's an extremely interesting um, potential scientific opportunity for LSST. The only thing is that the horizon to this detection of a binary going towards the merger, but not yet merging, is only of order of maybe 10 megaparsecs. So I guess it comes down to us being sufficiently lucky to see the merger of a dwarf-neutron binary somewhere not too far away from us. So we'll see. Maybe it will happen, maybe not. So I'm quite curious what will happen in the next 10 years from the LSST. So here in the other figure actually are the images of these white dwarf neutron star binaries and black hole white dwarf binaries that are observed in extragalactic or global clusters that are found near other galaxies than the Milky Way. And it's actually quite spectacular and interesting. So there are really these bright young sources that are much younger than in our galaxy, because with X-rays, when we look extragalactically, we can see many more systems, and therefore we can select younger systems. So, for example, one of them, RZ2109, actually is a very fascinating system where there is a once white dwarf that was turned by a black hole into a parsec scale oxygen nebula. So it's a very interesting thing. So we saw how white dwarf turns into a disk, but also there's a place where white dwarf had been turned into a nebula. So it's quite spectacular actually. Moving onwards, I also want to mention that many of these systems will be also observable as gravitational wave sources. For example, for LISA, in the galaxy, ultra-compact X-ray binaries are one of the key systems that it will be actually observing. So along with double white dwarf binaries, and for the missions that are sensitive in decihertz band, such as LGWA, they will see mergers of white dwarf neutron binaries up to distances of order of 100 megaparsecs. So in principle, there is a great scientific opportunity to see both mergers first in gravitational waves and then later with LSST. If LSST and LISA, or LSST and LGWA, the gravitational wave detector, happen to exist at the same time. We're still waiting for gravitational wave detectors to be constructed and launched, of course. All right, moving onwards, I want to spend a few minutes just talking about a completely different topic, which is called active galactic nuclei disk. I think it's just to add to just to maybe give a sense for the variety of things that LST will see. In fact, um, just white dwarf neutron binary is one of many, many, possibly tens of different new transients that LSST will discover. And well, here's an example from a completely different realm of AGN disks. So AGN disks are disks of gas around supermassive black holes at centers of galaxy. Here is an artist's impression of such disk, and it launches a jet, all right. And then here is an image which was really very hard to find when I was looking for it some months ago, of stars embedded in AGN disks. So first of all, we know that there are stars in AGN disks. We have observations of star formation in AGN disks. We also know of stars in our own Milky Way galactic center, which had an AGN phase, likely 100 mega years ago. So nevertheless, there's very little research on stars in AGN disk as populations. There's a lot of research on black holes in AGN disks. Well, there's this very few visualizations of stars in AGN disks yet. So I hope there'll be more soon. Anyhow, there are stars in AGN disks, and these disks, active galactic nuclei disks, are concentrations of gas. And when stars are embedded in gas, they can accrete material through the Bondi-Hoyle accretion process. So basically that happens when star gravitationally focuses the gas forms a shock behind the star, and then accretion disk around the star, and then lands eventually on the star. So this whole process of star gravitation attracting the material and capturing it and eventually accreting it is called Bondi-Hoyle accretion process. And one key thing to see is that the accretion rate is proportional to the square of the mass of the star and linearly proportional to the density of the gas in which it's embedded. But it's also extremely sensitive to the relative velocity between the star and the gas. In other words, if the star is at rest, then it's much easier to accrete the gas. And if the star is moving relative to the gas, and if the gas is hot, it's much harder to accrete the gas. And the thing is that for typical numbers that are relevant to active galactic nuclei disks, the star can accrete quite a reasonable amount of mass, about 0.8 solar masses, in approximately 1 million years. So it's been noted that actually the formation of main sequence stars by dwarfs and neutron stars that have accreted a lot of material from the surrounding gas actually is possible through this process. So it's one of the reasons why we actually expect explosions that might happen inside the disks of active galactic nuclei. So first of all, stars can accrete and become very massive, and we see evidence of that possibly in the Milky Way galactic center. And we definitely have theories for this happening in other active galactic nuclei. We also might expect that maybe in active galactic nuclei, double white dwarfs might merge, or maybe double neutron stars. And in all these cases, when they do that, a merger or an explosion or a core collapse supernova, we expect, well, something interesting going on in AGN disks. So here I would like to spend also maybe a minute and talk about the so-called circumstellar matter interaction. So it's the way that transients actually become bright, especially when they're produced by core collapse supernovae, the most typical supernovae produced by the collapse of massive stars. So what happens there is that there are outer layers of material of the star. For example, it could be a red supergiant, and then there is a core collapse and a shock wave launched from the center of the star. So there is material basically expanding at a very high speed, supersonically relative to the envelope. And as this material is expanding into the envelope that's at rest, there is a collision front between this expanding material and resting material. And at the collision front, there's a lot of heat released. And as a result, there is a rise in temperature, and eventually that excess energy should be radiated. So in fact, the generation of light in such types of supernovae is a combination of the shock producing the heat, the shock propagating out of the star, the whole thing expanding and becoming more optically thin, and basically this combination produces the light curves we see. And when a star explodes in the AGN disks, exactly the same thing happens. Actually, the star explodes. There is a surrounding material that basically the expanding ejector interacts with, produces shocks, and then these shocks are observed as, well, some transient on the sky, although transient will be coming from the active galactic nuclei. So we did some simulations of these with a two-dimensional code called Hormone, developed by Ryosuke Hirai. And these are just visualizations of explosions in AGN disk, so surrounding disk explosion and indeed a shock. And there can be quite interesting geometries happening in the disk after some time from the explosion. And if one constructs light curves, they look like this. Actually, it's again in LSST bands. So we constructed them with the so-called SNAC code, which is a lightweight light curve synthesis supernova code. So here's an example for a radiatively dominated disk. Here's an example for a pressure dominated disk. These are just two models that are comparably valid for active galactic nuclei. And here's an example for a starved AGN disk. So AGN disk that has been a fully developed AGN disk before, but now has lost much of its material. And we see that actually, well, there's quite a lot of transient produced initially blue, then later on very red or infrared. And this is in itself is actually quite interesting because LSST will be detecting approximately 1,000 of bright transient events from AGNs every year. These are called tidal disruption events. And when LSST is detecting thousands of events per year, the question is how often will it be finding peculiar transients that actually are caused by explosions? Because when you detect 1,000 things, maybe one of them, or maybe 10 of them, maybe even more of them will be actually unusual and anomalous. So this is something that I think is also really exciting that will come out from LSST and actually was already maybe coming out from ZTF. So I will not talk much more, but I just will point out that explosions in AGN disks are potentially another way of seeing what happens in those quite far away extreme environments. All right. Lastly, I want to mention the LISA instrument. The LISA is a gravitational wave interferometer, which is another mission that is going to be launched in 2035. LISA is a first gravitational wave instrument to be launched to space, and LISA will be sensitive to objects that move on timescales of about half an hour. In other words, it's sensitive in the millihertz domain, and it will be able to detect basically all the double white dwarfs in our galaxy, among many other things. So I'm mentioning these partly because I'm personally involved in LISA, but also partially because there's not enough awareness, I think, about it. But LISA we'll have extremely many science cases, many of which overlap with those of LSST. So LISA will see a large number of double white dwarfs. Perhaps LSST will see some in our galaxy. More relevant, perhaps, is that LISA will see mergers of massive black holes, and perhaps the merger of massive black holes might be associated with optical transients, and actually having a synergy or a simultaneous observation of the optical transient and the gravitational observation of the massive black hole merger or supermassive black hole merger would be extremely interesting. So in fact, this science case is extremely interesting both to LSST and to LISA. And then there are also extreme mass ratio in spirals that LISA will be also extremely sensitive to. So these are related to stars or stellar mass black holes, or perhaps maybe some white dwarfs spiraling into the supermassive black holes. And in fact, there could be quite interesting overlaps there too, because in fact, tidal disruption events and the quasi-periodic eruptions, the other X-ray transient that happens in galactic nuclei that follows tidal disruption events sometimes, might also be scientifically interesting or scientifically observable by LISA. So here I just want to highlight that if anyone in LST community has such interest or capacity, I would highly encourage you to communicate with people who work on LISA, because people in LISA are extremely interested in the scientific capabilities of LSST. So I guess here, little by little, we reached the end of my talk. So I just want to again say the key message I wanted to convey. It basically is that when we get higher sensitivity, we can expect a larger diversity of different transients, and we will be able to see transients that have been once thought unique and unusual, for example, those from white dwarf neutron star binaries, or those from explosions in AGN disks, and really many, many more. I really believe that LSST will impact many scientific fields, and LSST and other sciences will greatly benefit from multi-instrument synergies. Finally, I want to highlight that many people in LISA find LSST extremely relevant, and I encourage anybody to talk to the people in the LISA collaboration. All right, with this, I want to thank everybody for your attention.
Thank you so much. This was a super great talk. It's super interesting to see the huge diversity of transients that we don't fully understand. So thank you so much for this.